Okay, so solubility equilibrium. So we've already dealt with acid, base, gas. All have been homogeneous. Okay, but now we're going to start looking at heterogeneous equilibrium, which means we're going to be dealing with precipitation reactions, or, as you may remember from honors chemistry, double replacement reactions. Okay, and now we're going to actually put numbers to these things so we can actually tell whether something will precipitate or not, or whether the reaction will move forward. Excuse me. Okay, so let's just refresh our memory. We've been dealing with K, which is our equilibrium expressions. The K for solubility equilibria is KSP, okay? When we have a saturated solution, you have to remember that this is going to be a solution with undissolved solute. So you'll have your solution and you'll have solute sitting in the bottom of it. A solubility product shows how soluble the solid is in water. So if we have small KSPs, that indicate small amounts of solid will actually dissolve. And when I'm talking about small KSPs, most of these KSPs are to the negative exponent, so they're already small. So when I say small KSPs, I'm talking about to the negative 12th, to the negative 13th. That means really small amounts are actually going to dissolve. Okay, all right, solubility. Solubility is how many moles can we fit in a liter for a solution. The solubility of a substance can change, where the KSP for specific solids at a certain temperature will not change. Okay, so for example, if I have silver chromate in equilibrium, it breaks into these two ions. Okay, so the chromate ion, the molarity of the chromate ion is 1.3 times 10 to the negative 4th. Okay, I can figure out what the KSP is for this solid by setting up an equation. Okay, so ultimately what this means is if I have 1.3 times 10 to the negative 4th, that means I can fit that many moles of this ion in 1 liter of solution. Okay, that's pretty straightforward. Okay, but we also need to figure out what's the concentration excuse me, of silver based off of this concentration of chromate, because it had to come from the silver chromate. Okay, so you can say question mark, but ultimately I'm going to say for every 1 mole of the CrO4 negative 2, I can have 2 moles of silver. So ultimately silver's concentration is going to be doubled, which turns out to be 6 point, hang on, this math's wrong. So I'm going to do 1.3 negative 4 times 2, and I get 2.6 times 10 to the negative 4th, and that's my silver ions in concentration. And that over liters is then the molarity of the silver ions. Okay, so now that I have the concentration of each of these at equilibrium, I can solve for KSP. So you have to remember, solids are not going to be involved in equilibrium. So all KSP equations are going to be the concentration of our products. So then all I would have to do is plug in my numbers that I just solved for here. So I have the 1.3 times 10 to the negative 4th times the 2.6 times 10 to the negative 4th, and I'm going to square that because I have a 2 coefficient for my silver. So then when I plug this into my calculator, times 2.6 negative 4 squared, I get 8.79 times 10 to the negative 12th. And that's going to be the KSP for your silver chromate solid. Okay. You can also use KSP to solve for the solubility. So if you're given a KSP, how can you figure out what's the concentration that you have? And we're just going to rice like we've done before, okay? So if I'm starting with calcium fluoride, I'm going to have calcium fluoride solid in equilibrium, and I'm going to break that into calcium ion and fluorine ions, and then you have to balance, okay? So it's telling me that this is the KSP, so I can calculate the solubility of calcium fluoride by using that KSP. So I'm going to just rice. So initially, I'm not going to have any of the solid in my equilibrium expression. I have 0 of this, 0 of this, plus x of this, plus 2x of this because of the 2 coefficient. And then I'm going to have x, 2x. So if the KSP is equal to calcium times fluorine, and you have to remember fluorine is going to be squared. Let me zoom this out a little bit because it has a 2 coefficient. I can say 3.9 times 10 to the negative 11th times x times 2x squared. Okay, and then if you do this, you're going to have x times 4x squared, and then you have to remember that when you multiply x's, you add them. So it's ultimately going to be equal to 4x cubed, and then you can solve for x doing that equation. And then that gives you the concentration of each ion in solution. Okay, so that's how we calculate concentrations and solubility constants. There's also things that we can talk about, and this is section 17.5, that deals with okay, things that affect the solubility, like why won't things dissolve as readily, okay? And that's just going to mean this is where we're going to be dealing with the common ion effect, okay? So here, if we look at this example, if I add silver nitrate into the solution, I'm actually adding, this should say making more products. Oh, if I'm adding silver nitrate, that ultimately means I'm adding more silver ions, which just like what we did with Le Chatelier, if I increase that, it's going to shift it to the reactant side. Okay, so if I'm doing this calculation where if I'm looking for the molar solubility of calcium fluoride in this solution, what I'm going to have to realize is that I'm starting, if I'm given this, I'm starting with calcium already in the solution. So when I rice this, and I have calcium fluoride, just like we did before, in equilibrium with calcium ion and 2 fluorine ions, okay, it's solid, aqueous, aqueous, okay, when I start this solution, if I have 0.01 molar of calcium nitrate starting, instead of the calcium being 0, it's going to be 0.010, and this will be 0, and then this has nothing to do. And then you just set it up the same way. So it's going to be plus x plus 2x, so then we have 0.010 plus x, and then 2x here. And then what we're going to do, just like we've done before, is this x is going to be too small to contribute to the change in concentration, so we can ignore it when we solve, and then we can just set up our equation. So then we're going to have our KSP is equal to the calcium ion times the fluorine ion, and it's going to be squared. Okay, and then we can say 3.9 times 10 to the negative 11th is equal to, now calcium actually starts with something instead of just being x, so it's going to be 0.10 times our 2x squared. And then you guys can solve for x in doing this problem. Okay, the last thing that I want to talk about is solubility and pH. If a compound contains a basic anion, so this is the conjugate base of a weak acid, its solubility will increase as the solution becomes more acidic. Okay, So solubility of slightly soluble salts containing basic ions increases as the H plus increases as well. Okay, and then we'll look at an example of this when we do these problems in class. Thanks.